So to introduce, this is Joel Bombile. He's a graduate student from Pennsylvania State University, where he's co-advised by Scott Milner and Michael Janik. Joel grew up in the Congo and did his undergrad at the University of Cape Town before moving to the States for his PhD. And today he'll be presenting his work on modeling polymer semiconductors to understand charge transport properties, specifically for energy applications. So with that, I'll give the floor to Joel.
Well, thank you, Nicole, for the kind introduction, and thank you all for coming to attend my seminar. I'll try to project my voice because I hear my microphone is, but I'll try to project my voice. So it is really my pleasure to tell you about the work that I've done for most of my PhD, involving building a tight banding model to investigate the localization of charge carriers and excitons in semiconducting polymers. So semiconducting polymers are polymers with a backbone characterized by an alternation of single and double bonds, which allows them to have the pi orbital involving the double bonds to be delocalized over the whole polymer chains, and therefore allowing these material to have semiconducting properties or conductive properties. And they are used, they are at the heart of organic electronics, where they are used in a number of electronic devices, such as light-emitting diodes or field effect transistors and photovoltaic cells. And the idea in using this material is not to replace the organic materials such as silicon, but rather to take advantage of the unique characteristic that they offer that combine the electronic properties with high mechanical flexibility, the possibility of being solution processible and even printed on flexible substrate, and also potentially low material cost. And if you just take a closer look at a photovoltaic devices, one of the best performing device currently in the market is a bulk heterojunction solar cell, where the active layer of the device is made of a mixture between a donor and an acceptor, where the donor material is a polymer, and an acceptor can be a polymer or another, usually another small molecule. And within the donor material, a light is absorbed and an electron is excited from the highest occupied molecular orbital, and leaving a hole behind, to which it then combines through Coulomb attraction to form an exciton. And once this exciton form, it then diffuses to the interface between the donor and the acceptor material. And once it is at the interface, this exciton dissociates, and with the help of an applied electric field, it's the two charge carriers, the hole and the electron, separates. And once this separation takes place, the two charge carriers have to migrate to the interface, where they can then be extracted for current generation, electricity generation. So the performance of this device as a whole relies on all these different processes being optimized. Particularly, you will notice that in the first step and the last step, the ability of the material to conduct charges is critical, is important. Unfortunately, semiconducting polymers are known to have a very low charge mobility compared to their inorganic counterparts or compared to other material. And this is due to the fact that within this material, charges are localized, highly localized. it happens that the trend in this table here correlates with the structural ordering of the material. And for a long time in this field, people have tried to increase the charge mobility of this material by increasing the structural order of the material. But more recently, polymers with a complex, with more complex bone have been synthesized with showed a high mobility, and actually there was a jump of around, we were around from around 1 to 10, and seemingly less order is observed within this material. So this just highlights the fact that we need a clear understanding between the structure or structural changes within the material and the electronic properties in order to design devices with better performance. It turns out that studying the electronic properties of polymer material and particularly accounting for structural changes, one has to take into account the complexity of play between the electronic degrees of freedom and the nuclei degrees of freedom or the local environment within the material. And also, in order to study phenomena such as like charge localization, one has to look at large system sizes, and if one has to take into account disorder, one has to average over many configurations of the system in order to obtain a representative quantity. And these are prohibitive for first principle methods such as density functional theory or higher level quantum theories. So our approach our goal is to use a cost-effective model that is able to predict the electronic properties of polymers while maintaining a clear link between the structure and the structural changes within the material and the electronic properties. Particularly within this talk, I will focus on using this model to investigate the localization of charge carriers within semiconducting polymers. And I will also use the same model to study exciton, particularly how strongly they are bound, and also their dissociation and separation at a donor-acceptor interface. And my study will focus on this polymer here, polytyrene, as a model case. It was one of the most studied polymer in this field. And so the model that I'm using is based on the tight binding approximation. It is a semi-empirical model, and within this approximation or within this approach, a polymer chain is considered as an array of sites, and the site corresponds to an entire monomer unit. So we are coarse graining at the level of an entire monomer unit. And the energy of a charge carrier within this array can be captured by this tight binding Hamiltonian, where the first term here represents the energy of a charge carrier sitting on a single site. And the second term here captured how much the energy of the system is lowered when the charge carrier is able to spread out to the nearby site by quantum mechanical hopping. I should mention that these are you don't need to know the details of the equation, but these are the creation and annihilation operator. But this equation has two parameters, the on-site energy and the hopping matrix elements. We determined, or we parameterized this equation, determined this parameter by reference to first principle calculations. Here on the right here, you see that we have used density functional theory to determine the relevant parameter in the tight binding model by fitting the electronic structure computed using our tight binding model to DFT. And this is the band structure. It's simply a representation of the different electronic energy levels within the material, and particularly here is shown the fourfold valence band, and the valence band is simply the set of highest occupied electronic states as more relevant for the conduction of holes within the material. And this is a fourfold conduction band. Here again, conduction for the lowest unoccupied electronic state as more relevant for the conduction of holes. And I should mention that the parameters within this tight binding model are sensitive to changes in the surrounding environment of charge carriers. The on-site energy are affected by changes or distortions of the monomer units, and also by changes in the surrounding dielectric medium. And the hopping matrix elements are affected by dihedral rotations. So this is the dihedral angle between two successive monomer units, and among other factors. So over the rest of my talk, I'll show you how we use this model to investigate like the localization of charge carrier and excitons. For the localization of charge carriers, we have two different mechanisms by which charges within a polymer can localize. The first mechanism is through Polaron formation. And let me just explain what this is. This is when a charge carrier is able to distort its surrounding medium, and the distortion in turn interacts with the charge carrier attractively and tending to localize it. Essentially what happens is the charge carrier then redistribute itself spatially in a way, in such a way as to optimize the benefit of the attractive interaction with the distorted surrounding. And the second mechanism is through disorder, or also known as Anderson localization. And here, the inherent disorder within the material forces the charge carrier to adopt a special configuration or a special distribution that minimizes its energy. So I'll begin by first describing how we use our tight binding model to understand dihedral disorder, and I will particularly focus on dihedral disorder. So to be able to model this, one needs two different elements. The first is understand how dihedral distortion affects the electronic structure of the material. And the second element will be to understand what is the extent of dihedral disorder within a chain, a polymer chain in a given medium. So first, to understand how the distortion affects the electronic degrees of freedom, here we have a plot of the electronic charge distribution for the highest occupied electronic state as relevant for the conduction of holes within the material. So when you notice, we've done calculations. These are periodic calculations in a unit cell with 4 rings, and we have distorted the dihedral angle between the 2 middle rings. And what you notice is as the dihedral angle is distorted, we are breaking conjugation. And by the time we reach a dihedral angle of 90 degrees, we have completely destroyed the electronic pathway for conduction. So we captured this in our tight binding model, we have determined how the parameters that controls the hopping of charge carrier from one side to another depend on dihedral angle. The picture on the left here is this parameter is a function of dihedral angle for holes or for as relevant for holes for all conductions, and on the right it will be the same for electrons. So having captured that, we now need the second element is what is the extent of dihedral disorder in a chain, in a polythiophene chain in a given medium. And to do that, we turn to molecular dynamics simulations, and particularly we've done simulations for chains in the melt, and here is a picture for the simulation of chains for a polythiophene, a P3HT chain in a chloroform solution. And from these simulations, we extract the dihedral potential, and the dihedral potential is then used in this expression to generate the distribution of dihedral along a given chain at a given temperature. The dihedral distribution at a given temperature. And this dihedral distribution is used to populate the dihedrals for the chain in a given medium. And one thing to note is we have a different dihedral distribution depending on the medium in which the charge, the chain is found. The chain in the solution appear to be more disordered than chain in the amorphous melt or chain in the gas phase, as evidenced by the less uniform dihedral potential or dihedral distribution for the chains in solutions. So having the two ingredients that we need, we then used our tight binding Hamiltonian modulated by dihedral rotations to look at how the states, the highest occupied electronic state as relevant for the conduction of holes are in a chain in two different situations. We look first at perfectly ordered chains. So that would be a chain with devoid of any dihedral distortion. And within such chain, what we found is that the highest occupied electronic states are delocalized over the whole chain. As you mentioned, this is the wave function, and the best way to understand the wave function is when you take the square of the wave function, you get the probability of finding the particle in space. So this extended wave function gives us an idea that the charge carrier will be delocalized within such chain. And for chains in solution with dihedral disorder, we find that these same states are highly localized. And particularly, we observe that the charge carrier decide to sit in the region of the chains with the highest hopping matrix elements, or in other words, less distortion from planarity. So we went a step further to try to see how dihedral disorder will affect a measurable property. Particularly, we wanted to capture the extent to which dihedral disorder contributes to the broadening of an absorption spectrum. So to get an absorption spectrum, again, we look at excitation due to light absorption of electron from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. But here we have an extended polymer, so instead of having one state or like one or more, we have a set of of highest occupied electronic states that will be part of the valence band that will be involved in these excitation that form the absorption spectrum. And what you need to get this absorption spectrum are the excitation energies. So that will simply be the difference in energy between the initial state and the final state. And we also need the probability of this excitation to occur, which are simply given by the transition dipole moments. And we have these two ingredients from our tight binding model, and we can compute the absorption spectrum. So we've done that for a all trans chain, so that is a perfectly ordered chain. And what we see is the absorption spectrum, or the absorption peak, is rather very narrow. We have a very narrow absorption peak. And when we did that for chains in solution, and here we have averaged this absorption spectrum over a large number of configuration of the chains. And what we observe is that simply by dihedral disorder, simply by taking into account the dihedral disorder, we are almost reproducing the entire broadening of the absorption spectrum that experiment reveals. And this only highlights that dihedral disorder alone play a significant role in impacting the electronic properties of a polymer chain. So I'm just going to switch gear here now to look at the second mechanism of localization, and this is through Polaron formation. So we've also looked at Polaron formation in this material, and I will go again quickly explaining what Polarons are. Polaron form when a given medium is able to reorganize in response to the presence of an excess charge. So an extra electron or the absence of an electron. And they occur in ionic crystals where the ions around the excess charge will reorganize. They can occur in one-dimensional polymer chains where the nuclei will distort in response to the charge carrier. And they can also occur in a polarizable medium where the surrounding dielectric will reorganize in response to an excess charge. So the energy of this polaron can be captured in three different terms. We have the energy of the excess charge and the energy of the responding modes within the material, and the interaction between the responding mode and the excess charge. And at equilibrium with respect to the responding mode, these two terms give us the stabilization energy that occurs as a result of this Polaron phenomena of Polaron formation. So I'll look at, over the next 4 slides, look at these, the Polarons that arise through the reorganization of nuclei and Polarons that arise through the reorganization of the surrounding dielectric. Quickly for Polarons in a one-dimensional chains with the ions reorganizing or the nuclei reorganizing, we have two terms that are part of the Polaron formation. The first one is the energy of the charge carrier that we were able to represent with our tight binding model. And here, these A are the amplitude of the wave function on a given site. And the second term here is the stabilization energy that comes from the reorganization of the nuclei within the chain around the charge carrier. And I should mention that this first term is like the hopping term tends to delocalize the charge carrier. And the second term here, the stabilizing term, wants it to be confined in a small region of space. And upon optimization, I should mention that we determine the characteristic constant for the reorganization of nuclei using first principle simulation based on density functional theory, and we are able to determine this constant. And through the competition of these two terms, we have an optimal size of the polaron that will arise, and particularly we found that polarons that occur through this mechanism are localized over just about 10 rings with a binding energy of 10 millieV, which is rather small in comparison to the thermal energy at room temperature of around 25 millieV. So we've also extended this analysis to a two-dimensional lamella, where in addition now to the carrier hopping along the chain, it's now able to hop between chains, and therefore we have an additional term here that wants to delocalize the charge carrier, and we still have our stabilizing term that comes from the reorganization of nuclei. And what we observe for this system is that the polaron binding energy is positive, meaning that the polaron will not form in this system for P3HT. And to understand or to rationalize that, we looked at how the binding energy for such a configuration will depend on the parameters that set its size. And what we found, we have two regions, a stable region and an unstable region based on, depending on the parameters. And polythiophene happen to fall indeed in a region where the polaron is unstable. This is what a stable polaron will look like in this system. So I was warned about this alarm, so I will keep going. And next, we looked at a different mechanism. Now, this is the polaron that formed through the reorganization of the surrounding dielectric medium. That's the picture there. And here, the polaron forms as a charge carrier induces a polarization in surrounding, and the induced polarization then interact attractively with the charge carrier and tending to stabilize it. And we consider the charge distribution as an array as a superposition of local charges, much like in the spirit of the tight binding approximation. And one can capture the energy of this system through a sum of pairwise interaction. So we have the charge interaction, charge dipole interaction, and dipole-dipole interaction. It turns out that the stabilization energy, the energy that dictates the stabilization of the system, is given by the polarization energy of the system, and that is because this charge distribution represents the quantum mechanics of a single particle which cannot interact with itself. However, at equilibrium with respect to the induced polarization, the polarization energy here can be obtained in terms of the electric constant of the medium and also the interaction of the charge distribution with itself. So this is what the polaron, the dielectric polaron energy we look at will have the two terms that wants to spread out the charge carrier, and here is the stabilizing term, actually the polarization energy that wants to stabilize the charge carrier. And here we used a dielectric constant that reflects only the electronic contribution to the polarizability of the medium. And what we found is that the charge carrier are localized by the reorganizing dielectric to about one chain with only a small leakage to the surrounding chain, with a rather strong binding energy of as much as half an eV. And this is rather large. And we've looked for evidence of such large bipolaron binding energy by looking at charge modulation spectroscopy, IR spectra, and these spectra reveal a Polaron stabilization energy of indeed around half an eV, and this suggests to us that the main mechanism for Polaron formation is through the distortion of the surrounding dielectric medium, and this mechanism is only supplemented by nuclei relaxation only supplements this mechanism, and this is because through nuclei relaxation we have observed that we have very small Polaron binding energies. So in the last part of my talk, the last 10 minutes, I will explain how we use the same tight binding methodology to investigate the excitons in semiconducting polymers, particularly how strong they are bound and how they dissociate at an interface. And excitons are an electron and hole pair that are bound by Coulomb interaction. And they form when light is absorbed in the material, exciting an electron from the HOMO to the LUMO, and the two leaving a hole and the two particles combine to form an exciton. And so this exciton, when it's dissociates within the material, it separates into individual charge carriers that are stabilized by the surrounding medium within the material. And we've looked at the surrounding the dielectric effect and the reorganization of nuclei. So to capture the energy of this process, we'll have the energy of the two charge carriers, the kinetic energy of the two charge carriers. We'll have the stabilizing effect that comes from the surrounding environment within the material, like ring reorganization and polarization energy. And we'll have the Coulomb attraction between the electron and the hole. And here, this equation, not to give you too much details, just to show that we are able to represent the Coulomb attraction between the hole and the electron with just one additional parameter that needs to be computed using first principle method. So we first look at an exciton in an isolated chain. So that is, we'll look at an exciton that obtained without any contribution from the surrounding, or any contribution of the stabilization coming from the surrounding medium within the material. And for such an exciton, we have an exciton binding energy, and the way to understand the exciton binding energy is just the difference between like the energy of the HOMO and the LUMO and the exciton binding energy and the exciton state. So we have an exciton binding energy of as much as 2 eV. And we have obtained to show that our results make sense. We looked at a first principle method that has been proven to reproduce excited state properties with accuracy, and we have indeed a very close agreement. So next we look at an exciton in a polymer film. And what we observe is the binding energy, and here it will be in a single crystal. And we have observed that the binding energy is reduced by as much as 1 eV. And to understand what happens why we have this reduced binding energy, the reference state for the exciton is no longer the HOMO and the LUMO, but rather the two individual Polaron state. So the carriers stabilized by the Polaron, and we have a smaller binding energy. A better way to look at this is to look at the Exciton dissociation potential. And so this is a potential that is obtained by looking at, I don't know, it doesn't look. Yeah, this is a potential that is obtained by computing the energy of the exciton at various separation distance between the hole and the electrons. So that will be for that configuration, and this will be for that configuration, and when they are completely separated, will be here. And so the exciton binding energy will be the difference between the optimal exciton, where we have zero separation between the charge carrier, and the completely separated carrier stabilized by the medium. So what happens is the polarization effect, or the stabilization of the medium, has led to a reduction of the binding energies of the material, the binding energy of the exciton. So next we look at what happens when we apply an electric field on this exciton. We observe that the electric field increase the separation distance between the two charge carriers, as shown in this figure. We have an increased distance between the hole and the electron as we increase the strength of the electric field until we reach a value where the exciton is completely unbound. And the field strength for the system we are particularly looking at is rather large, of 5 millivolt per angstrom. And to understand this, or to rationalize this, we wanted to see how is the exciton dissociation potential affected by the electric field. So this is a second alarm. It turns out that the electric field interacts differently with a positive charge versus a negative charge, and it results in tilting the exciton potential. So this is when we have no field applied, and when we apply a field, the potential is increasingly tilted. And the electric field that's just managed to suppress the minimum in the exciton potential is able to unbind the two charge carriers. And we have observed that the field that is just able to unbind the charge carrier is directly related to the largest force of attraction between the charge carrier, as given here by the largest slope in the exciton potential. So next we look at what happens when the exciton is at a donor-acceptor interface. And here we'll look at particularly the effect of the energy of sets, and that is the difference in energy between the highest occupied molecular orbital between the two sides of the interface, so the donor and the acceptor side. And as this level of set is increased, we observe that the separation distance between the charge carrier also increase, as you have evidence here in this plot where we plot the probability, the distribution of the two carriers. As we increase the energy level of set, we can see that the two carriers are pulled apart. And to understand this again, we look at the exciton dissociation potential, and particularly at the effect of this energy level of set at the interface. And we observe that the potential is tilted by the level of set at the interface. And this occurs because this interface, the level of excited interface introduces a bias for an electron or a hole to be on one side of the interface versus the other. This is because holes prefer to be on the higher HOMO, and electron prefers to be on the lower LUMO, so lowest occupied molecular orbital. And this has the effect to reduce the electric field strength that is necessary to unbind the charge carriers. And this is, as you can see here in this figure, where we plot the field strength that's just able to dissociate the charge carrier as a function of the size of the level of set applied at interface. And we see that we require a less and less strong field as the offset is increased. So with that, I will summarize my talk. I've shown you a simplified model based on the tight banding approximation that we use to investigate the electronic properties of semiconducting polymers with a link to the structure or structural changes within the material, and something that is difficult to perform with using first principle methods such as density functional theory. And I've also shown you that the distortion of dihedrals within the material is a strong source of localization of charge carriers through the mechanism of disorder. And I've also shown you that dielectric effects are a potent mechanism for Polaron formation in these materials. And we've also looked at excitons as an electron and hole pair bound by Coulomb interaction and dissociating and separating to 4 Polarons. And I've also shown you the effect of the electric field and a donor-acceptor interface on the exciton, which pull the charge carriers apart, making it easier to be unbound. With that, I would like to thank you all for your kind attention, for your interest in my research, and for the amazing opportunity to come here and share it with you. I'll open the floor to questions. Yeah.
I had one where you showed the absorbance spectra between, your ideal ordered state, the solution, and the actual data. So I'm a little naive to this field, but my understanding is that you have a solution that's polymer, and you sort of crystallize it and evaporate it and then anneal it. So is the assumption that the order you're sort of calculating in your solution translates directly to the solid film? Or can you comment on that transition?
Yeah, so this is a UV-vis absorption spectrum for a polymer chain in dilute solution. So the measurement is done in dilute solution. Obviously, they are able somehow to subtract the effect of the solvents. So essentially what you're looking at is the absorption spectrum of the polymer chain itself. And the point of this graph here is why is the absorption spectrum broad? It is broad because of when the measurement is done, you don't have a single polymer chain, but we have like many polymer chains in solutions with different configurations. So the broadening is a result of disorder within the material. We wanted to understand how much of that, how much of the broadening of the absorption spectrum come from dihedral disorder alone, to understand how much dihedral disorder is important in terms of affecting the electronic properties of the chain. So this is what we've shown here. We've shown that we don't capture the whole broadening simply because obviously dihedral disorder alone does not represent all the disorder, but it represents a significant part of it.
When you showed the dihedral potential of the P3HT in chloroform,
yes,
I noticed there was a really sharp peak right at 180 degrees.
Right.
What's that all about?
So that I'm not entirely sure what are so it turns out that in our simulation the chains didn't stay much in exactly that position. That's why
It wasn't there in gas phase and melt, so there had to be some sort of connection to the solvent, right? That was
Right.
what I thought was curious.
Yes, there could be some sort of connection with the solvents, and this illustrates why it is important to actually look at what the dihedral distribution will be like for the chain in a medium, and not just translate a dihedral distribution from chains in the gas phase or in an amorphous melt to the solution.
Any more questions?
I've got one more. So towards the end, you showed the interface between the donor and acceptor
Yes.
domain, that interface.
Yes.
And I don't know if I'm totally right on this, but I would guess there would be a space charge region on both of those sides, where the populations of each charges are kind of deflected according to like Fermi level and band bending around it. Anyways, so what I'm wondering is if you find the length of that space charge region and the potential difference in that region, does that correspond approximately to the fields that you were applying kind of externally to get that charge separation? I guess what I'm getting at is, do you think kind of a space charge region electric field in addition to an applied external field adds up to 25 millivolts per angstrom?
Yes, yeah, exactly. So this, actually, this figure, the next one is, so this shows that, yes, you can obtain charge dissociation and separation by just applying an external field, but you require a pretty large field in order to obtain that. And the reason why it is important for charge carrier to migrate to the interface is that the exciton, not the charge carrier, the exciton to migrate to the interface. And it's because the interface, because of that level offset, we have a very large, I guess it's a large local field, if I can say, that by itself, without any externally applied field, is able to pull the charge carriers apart. So it pulls the two charge carriers, actually. It pulls the two charge carriers apart, as you see here. And then with when you apply, you now require, because the charges are already pulled apart by that interface, you now require a smaller electric field to be able to unbind the charge carriers. But obviously, in an actual device, you don't go to such big, like a level of offset, because a large level of offset will mean that you'll have a small open circuit voltage. So there's a trade-off.
Any more questions for Joel? Okay, if there's no more questions, make sure you fill out that form, and then Norio and Emily, and Norio will be collecting them at the door, and then join us for the happy hour session in the lobby.
Thank you.